TUBS-IRMB. Digital India. Educated India.
So, what we do now is the last lecture where we deal with the actual kinetic theory and its connection to the Navier-Stokes equation. Yeah, so this is important to know what part of kinetic theory we actually have to carry over to the Lattice-Boltzmann world in order to solve the Navier-Stokes equation. Yeah, because what we are going to do with Lattice-Boltzmann is to solve the Boltzmann equation in the hydrodynamic limit, such that we get the Navier-Stokes, that we actually solve the Navier-Stokes equation. So, and for this we remind ourselves of the BGK equation without forces to make our life simpler. So the BGK equation would be the time derivative of f and this microscopic advection operator on f, and now the collision operator is given by the BGK form, which is f equilibrium minus f driven to the equilibrium by tau. And we have not yet really said accurately what that tau is. So tau, what is tau? Suppose we have here particles, so these are supposed to be particles that are coming and colliding, and they have a tail showing you where they come from. So they will meet here, and then one of the particles will be kicked out where this particle meets another particle and will again be kicked out of this line until it meets another particle. Yeah, and here, so this is the one particle that originally started here. So I could potentially give it a different color, like this is the blue one. So it went through all of this. So the distance that particles travel during on their way, this differs, but you can imagine that there is an average distance that they would travel, and this average distance is called here lambda, and this lambda is the mean free path. So the average distance that the particle travels before it crashes into another particle. So actually you can put some brackets around here because we'll later call this thing only mean free path. Lambda is mean free path. So of course the particle has a velocity, and this velocity as is the mean is called z, the mean magnitude of particle velocity. This is of course it's also called the terminal velocity, not the terminal, but the terminal velocity, because it's basically given by the temperature. So the higher the temperature is microscopic kinetic energy. Yeah, energy is mass, is 1/2 mass times the velocity square. Yeah, so this is basically the square root of this is its terminal velocity, and this is now here called z, particle velocity. And then there is, of course, this relationship that the path traveled is the velocity times the time, right? So this tau is then the mean free time. Mean free time between collisions. So this c, this terminal velocity, is roughly, not necessarily exactly, but roughly the speed of sound, or it is related to the speed of sound by a constant. Yeah. So we'll call this here speed cs, speed of sound. Okay, now this is tau, and now we look at our system in a way that we think is important for us. So we do we look at the dimensionless numbers using Buckingham or pi theorem, however you want to call it. So you have probably done dimensional analysis. Yeah, in particular, if you have studied fluid mechanics before, then you know that that you can describe your system. Yeah, so systems that fluid dynamics guys like are, for whatever reason, cars moving with a velocity u and usually having a length L, then you can describe your thing, what you want to model, with dimensional quantities. With u being a velocity scale. This is not necessarily the velocity of the vehicle. It's just a characteristic velocity that you use for describing your system. So for example, you could say this is 1 meter per second, and you have a length scale for example 1 meter. Okay, so the track would potentially be more than 1 meter. So now dimensionless numbers. So these are dimension carrying numbers, dimensionless numbers describing our BGK equation. Are the Knudsen number. The Knudsen number, by the way, in fluid dynamics guys, do you know what Knudsen number is? Yeah. Lambda by L, okay. Yeah, lambda by L, because you can do all fluid dynamics without talking about Knudsen number at all, right? Yeah, so this is yeah. So this is the Knudsen number. And then, of course, you have the Mach number. And this is the velocity by the speed of sound. So many people know this. By the way, Mach was a guy who up till his death never believed in molecules. Yeah, so he was one of these guys who absolutely believed in continuity. So he would not be happy that we are using his name that much for kinetic theory. So of course, you can turn these things around. Lambda is the Knudsen number times your large length scales. CS is velocity divided by Mach number. And now since tau is lambda divided by CS, you can determine that this is the Knudsen number times the Mach number times some length scale divided by a velocity scale. So this describes your tau. And what we are going to use is that both these things, the Knudsen number and the Mach number, are for what we describe as continuum limits, yeah, are both small. So the Knudsen number must be small. Particles need to be close enough together, yeah, to so they must have a short mean-free path. So Knudsen number would be small, and Mach number would be small when velocity is small. So the incompressible Navier-Stokes equation assumes that the Mach number is 0, right? So then for this hydrodynamic limit, these two numbers would be small. Right, this is what we wanted to write down next. Limiting cases. So in continuum, L must be much larger than the mean free path, meaning that the Knudsen number is going to 0, and we are dealing with slow flow because slow flow can be considered to be incompressible. I mean, this is not completely true. If you have slow flow through porous media, airflow through porous media, yeah, this can be pretty compressible, even though it's low. It's low Mach number and very compressible because the resistance is so high. Yeah. So here the assumption is that U is much smaller than the speed of sound, and this would imply that the Mach number is going to 0. So, and now what we are interested in is this incompressible continuum limit of the BGK equation. Again, BGK is dTF plus C into scalar product on nabla F FEQ minus F, and this divided by tau. So of course, you know what this means. This is xi upsilon zeta into dx dy dz with scalar product. So what you can now write is that this is dt plus xi dx f plus upsilon dyf plus zeta dz f, and you can put the rest on the other side. There's minus FEQ minus F divided by tau, and this is equal to 0. So we put everything now on one side such that we can take moments of this side here and moments of this side here. And when we take moments of 0, we always end up with 0, right? So we can take moments of the equation and we always know that they will be 0. So as a reminder, countable raw moments, M, A, B, C. Okay, I'm a little bit running out of letters. Now we have C as two things, C as velocity and C as index here. Yeah, usually we don't, they are so in different places that we don't get too much into collision with this, yeah? But it would be strange if I say A, B, D or something, right? So this is Fxi by the power of A by the power of B and zeta by the power of C dxi. So this is how we define the moments, and instead of using the function f, oh wait, there should be f here, right? Nobody complained. How comes nobody complained? I'm sure at least 80% of you do recognize this, right? Okay. You didn't? Yeah, okay. Yeah, I know I said in the beginning when I write nonsense, then just correct it. But you can, point it out. So now instead of taking moments of the distribution function f, we can also take moments of the entire equation. Moments of the BGK equation. So this obviously reads like this. So we would have xi by the power of A, epsilon by the power of B, and zeta by the power of C into dtf plus dx xf plus dy epsilon f plus dz zeta f minus f eq minus f divided by tau, and this integrated over xi. All of this is equal to 0. So you see, I've taken the liberty of putting xi inside this derivative because xi is a coordinate, therefore constant, and I can just put it in here because its derivative is 0. Yeah, it doesn't matter whether I put it in front or into the differential here. And the same thing is of course true for these guys. Yeah, since it's the same for these guys, and they are all not dependent on x, y, and z. What I can do, I can define equation 4.1. So see, now there's now something important happens. Yeah. So I can take all of them together and plug them into this place. And then I take this, also the integral inside, and see that I will produce a certain moment, and I will have the time derivative of that certain moment. The moment I have the time derivative of dt is the moment MABC. Yeah? So then the same thing happens here where I have a spatial derivative of this guy together with this guy. Yeah? Now I have again xi by the power of a, epsilon by the power of b, zeta by the power of c, but I still have one xi here. And now you will see how useful countable moments are. Yeah? Because you see we have xi comes with a plus 1. This means this index is a plus 1 and b, no, without comma, with b and c, right? We get this. This is very important. So plus dy. Now if you've once seen it, then it becomes very easy, yeah? Because here's one epsilon more, right? So it will be b plus 1 c, and it will be d z m a b c plus 1. Okay, everybody following? Then here we will just have the usual moment. So we'll have MABC equilibrium minus MABC, and this divided by tau. And all of this together is equal to 0. Oh, sorry. I'm sure you've seen it. Minus. So now we turned the equation from this distribution function into equation for moments. Yeah? And this is a hierarchical equation for moments because we have not specified what A, B, and C is. Yeah? But we see if we want to calculate the time derivative of MABC, we need other moments. Actually, this leads to what we call a moment chain. So the moment chain. So what we can do now in order to see how this functions is simply to choose values for A, B, and C, and what else would we start with than saying that we start everything from 0. Yeah? A equal to 0, B equal to 0, and C equal to 0. So then what we get is dt m00 plus dx m100 plus dy m010 plus dz m001. And I now take the collision operator again to the other side, saying this is m000 equilibrium minus m000 divided by tau. So this what is actually m000? This is the integral over xi by the power of obviously 0, epsilon by the power of 0, zeta by the power of 0 into f d xi, and this is rho, his density. So somebody pointed out during the break that I'm not accurate here because I sometimes call this first moment the mass and sometimes I call this first moment the density. This is a little bit, you know, because Lattice Boltzmann guys already think in simplified physics, so to speak, so that density and mass kind of becomes the same, because otherwise I would always have to say that we don't actually have momentum as the first moment if this is density, but we would have momentum density. Yeah, So we are sorry for this. I believe if I tried to always make it correct, I would still do it wrong. So I'm explaining now that this that we simplified this a bit and say that this is the mass of this function together in this small volume that we are looking at, and because we are looking at this in the small volume that is related to the collisions, this is actually per this volume and therefore the density. Yeah, if you take this volume somehow into account, or it is the mass if you don't take this volume into account. And because I'm lazy and used to this, I sometimes say it's blah 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 density, or it's just the mass. Yeah. So sorry for that. If it looks a little bit inconsistent, yes, it is inconsistent, but this is the way it's usually used. So by the way, this thing, yeah, you could say density is of course not conserved because it could be compressed, but if it was mass, so the zero moment is conserved. And what does it mean for this to be conserved on the right hand side? It's zero, yeah, because M00 equilibrium is the same as a non-equilibrium. There they will disappear. So the M100, yeah, so this is what, of course, we have seen now a couple of times. This is rho. So, I mean, M100, we compared to one of the other moments that we saw yesterday, I'm not dividing by rho, right? Because I'm not dividing by rho, it's not normalized, and therefore it is rho, yeah, whatever rho was before here, it is this rho, yeah, times the velocity in x direction. And then we have, of course, M010, which is v times rho, and M001, which is w times rho. So, and because this thing is conserved, we have M000 equilibrium is equal to M000. So now you can write the thing like this. You get dt rho plus dx rho u plus dy rho v plus dz rho w is equal to 0. And you can rewrite this in a more compact way, that dt rho plus Laplace, the divergence of u is equal to 0. So anybody doing fluid dynamics has seen this equation? What is the name? This is the continuity equation. So the continuity equation drops out of kinetic theory. Plausible. You can derive the continuity equation without kinetic theory too. So going one step further, saying that we now look at A is equal to 1, B is equal to 0, and C is equal to 0. So what do we get? We get dt of M100 plus dx of what moment? M 200, yeah, plus dy M 020, No, no. What did you say? 110, yes. 110 plus the set M 101, right? So, you know, countable moments are amazing, right? So you can, you learn this in 5 minutes. So M100 equilibrium minus M100 divided by tau. So we have momentum conservation. Because we have momentum conservation, the equilibrium is the same as the equilibrium of M100 is the same as M100. Yeah. So this is, should I write it down? M100 is rho u conserved. Therefore, M100 is equal to M100 equilibrium. So, does this help us? Actually, now we need to know what is M200, right? So this is what we have not looked into it. So what that is, this thing? Well, easy, we get it when we say that A is equal to 2, B is equal to 0, and C is equal to 0. Then what we have to do is to say that this is dt M200 plus dx M300. I guess now you all can just write these things down. D sets M201, and this is equal to M200 equilibrium minus M200 tau. So, question. Is M200 conserved? It's a bit of a trick question, could be. So what is M200? It's a part of energy. That's a good answer. Yeah, it's only part of energy. Energy is conserved. Is part of energy conserved? Part of energy is not conserved. Only energy is conserved, right? This is everything. Everything conserved is part of, is not conserved, right? So, because it can go to the other parts. So this means that this M200 is not conserved. So because what is conserved is M200 plus M020 plus M002. So now this is energy, and that would be conserved. So nasty, it is, there's something conserved, but not the thing we are looking at. So, for that reason, because this is not conserved, we can actually do something fancy. Namely, we can solve this equation for M200 without any derivatives, because we have this here, right? So we solve this for this M200. So we can say that M200 is equal to M200 equilibrium minus minus tau times dt M200 plus dx M210 plus dy M120. Am I still? I'm doing something wrong. I'm doing a lot wrong. So did I get it right now? Yeah. So, and for all the other moments, now since we are practiced, for all the other moments that we had in this equation before, so the equation we were looking at, there was this M110. If we want to have this M110, this behaves the same way because this BGK equation treats all the moments the same. So here we have M110 equilibrium minus tau, and here comes dt M110, right? We are applying just the same logic as before that we've already practiced. So let's see dx. So what moment comes? 2, 1, 0 plus dy 1, 2, 0, and then the sets and 1, 1, 0, 0, 1, no, 1, 1, 1. Do you know what this means? 1, 1, 1, 1, 1. Do you know what it means that 1 Smith, 1 $2? So 1 is a guy who is called 1, and he won 1 Korean won. So 1, 1, 1, 1, 1. Sorry, I should keep these things out of the cut this out. So we have one more. That is M101. That comes with obviously 101 equilibrium minus tau dt M101. So it's 101 plus dx M201 plus dy M111 plus dz what is it? 102. Okay? Now we have all these equations. Now the equilibria of this thing we can compute from so equilibria is M200 equilibrium. Here we use the Maxwell-Boltzmann distribution rho divided by 2 pi kb divided by the mass of the particle and the temperature to the power of 3/3 e by the power of xi minus u square mass of the particle divided by 2k Boltzmann t. Now, okay, last time we said we are already centered. Yeah, this time we'll have here an offset velocity. And this we have to multiply with xi square and integrate over xi. And what comes out is rho kbt divided by m plus u square rho. So with regards to M110 equilibrium, we can do it the same way. But I was wondering whether you remember what we did in the morning. Yeah? So we can use this, I mean, and believe what Mathematica delivers us, but this morning we discovered that we can factorize these moments. So then equilibrium moments. So can you tell me now, without solving the integral, what M110 equilibrium would look like? Long integrals. Long integral simple solution. Okay, you remember we had to divide this by M000, right? So, and then we discovered that we can factorize them. Factorization means this is M100 equilibrium divided by M000 times M010 equilibrium divided by M000. Yeah? So what does this mean? So what is M100? I think we just wrote this down. Is rho, okay, so we have this rho u, and then this is rho v, and this is divided by rho square. But we are interested in what is what is this, and this we have then to multiply with rho again, so it will be rho u v, right? And obviously, this implies that M101 equilibrium is rho u w. Yeah? Okay, so this is the benefit of going through, you know, this morning, that we can just write everything down. Yeah, so I mean, I know we go through a lot of moments and integrals and all of this, but all of this is for the purpose that when we come to building up our lattice Boltzmann model, we directly understand how everything, you know, fits together. Yeah. Okay, so these are the equilibrium moments, and here we still have this problem that we always need to go further, but let's try not to go further, because I have an idea. Namely, we could say that tau being equal to Mach and Knudsen times the size of a system. Now what we're assuming is that system to be large and Knudsen to be small, Mach to be small, and therefore tau to be small, right? So when we assume this, everything that is left is only the equilibrium, because all these guys here, back here, they will disappear, right? So under this assumption, we can write that the time derivative of M100 plus dx M200 equilibrium plus dy M110 equilibrium plus dz M101 equilibrium is equal to 0. And now we can put these equilibria, all of them, into the system. This will be rho u plus dx rho k Boltzmann t divided by m plus u square rho plus dy u v rho plus dz set UW rho is equal to 0. So now we have, we now have products of which we take derivatives, so we have to apply the product rule, yeah, and sort things out. So I'm applying the product rule and I'm applying a certain order to this. So let's say in this first line, okay, so there's one interesting thing here. I have here u square, so there's u in it. I have here u and here u again. So I can always take u out first. So I'll have here u. By the way, the same thing here. I have rho times u. So I take u out and have u dt rho plus u dx rho u plus u dy rho v plus u dz rho w. So this was the first part. Now we have to take the second part. The second part is then rho dtu plus rho u dxu plus rho v dyu plus rho w dzw. Different brackets. So, and all of this is equal to okay. So it's not equal to 0 because I've left out this guy. So I put this guy to the other side, minus dx rho k Boltzmann t divided by m. So first thing to notice is when I take everything that is in that particular bracket, I can simply take the u out. And what I'm left with is dt rho plus divergence rho u. Now, you've seen this before, yeah, as the continuity equation, that this here is equal to 0, and with this, the entire thing is equal to 0, right? So all of this above here is equal to 0. And what we are then left with is rho dtu plus rho u into nabla u. So u, okay, here we have to distinguish that this is the vector u and this is the component u. Yeah? So this is without vectors, not a mistake. This is equal to dx rho k Boltzmann mt. So, do you know this equation? So there's something that we have to take into account in order to recognize this equation, namely that we need an equation of state, and we do this for the ideal gas equation. So the ideal gas equation has P, P pressure times volume is K Boltzmann. Yeah, that's the Euler equation, right? So with V, so because the rho, in the rho, we only counted the particles. We did not give a mass to the particles. This is why actually rho in this definition is just the opposite of the volume, yeah, because this is the particle density, so it's the number of particles per volume and not the mass per volume, yeah. Therefore, this will here disappear, and we'll have the pressure being equal to rho k Boltzmann t. So that's, as your colleague just pointed out correctly, this goes to be the equation rho dtu plus rho u times this u is equal to minus 1 over m dxp. So, as was pointed out already, we are a little lazy with when we use mass and so on, and yeah, so we often say, okay, mass is 1 and this disappears, then it's maybe not completely consistent with the units, yeah, so, but this would now look like this here. And this is the Euler equation. This is the Euler equation, yeah. So what you have is the material derivative of u on that side, and on this side you have the gradient of the pressure minus the gradient of the pressure. This is the Euler equation. Okay, so the Euler equation comes out. Is this what we want to solve? We like to have diffusion, right? So let's look at diffusion. So why don't we see diffusion? We don't see diffusion because tau actually is larger than 0, and we assumed that it would be 0. So tau larger than 0 in reality. So we have to take everything else into account. So we take now the liberty not to repeat all the calculations that we've already done, but we'll take everything that we've already done, write it down, and then we add to this sorry for moving here, we add to these remaining parts, right? So, and what I have to remind you is that we took the x derivative of that, the y derivative of that, and the z derivative of that. Yeah, so this is what we have been seeing here, up here. Okay, so we now can simply say, so tau does not depend on anything, so we put it in front, that this is dx. The rest here, dt m200 plus dx m300 plus dy m210 plus dz m201. So this is the first part, plus tau dy dt m what is it? 110 plus dx 210 plus dy m120 plus dz m111 plus d tau dz dt m. What's here? D1 M101 plus dx M201 plus dy 1 M111 plus dz M102. Okay, you can hardly read it, but I think you now know the system. Everybody, did I make it correctly? Okay. So we call now, for simplicity, this thing here S. And now we have a real problem that previously we could somehow circumvent. Yeah, we said that tau is not equal to 0. Now we have here, we have here the derivative of M300, yeah, so we can, of course, simply compute this, but this leads to what we call a closure problem. So if you have fluid dynamic guys, you will probably associate. You have a question?
From Euler's equation, how do you get the
The what equation? So you may use the microphone.
Yeah, from Euler's equation you wrote above.
Yes.
Yeah, how do we get the S terms?
No. We don't get them from the Euler equation. No. See. Okay, I try to explain. So we took, not that. So we took this equation, right? So in this equation we have to plug in M2 0, and so these three moments. Yeah. So now we computed what these three moments are, like this. Then we decided that we set tau to 0, and when we set tau to 0, we'll only have these things. Now we recognized that we were cheating, and we wanted to, uncheat this. Yeah, and for uncheating this, now we add these guys here again, and this is leading to S. So of course this is so the thing is we've cheated up to here, but we say, okay, so what we computed already while cheating, this we can still keep, yeah, but we have this as the reminder. Okay, making clear? Good. So closure problem. So the fluid dynamics guys among you know the closure problem from turbulence. Yeah, I guess so. You've heard this. The closure problem of turbulence and this closure problem are actually the same. Yeah, so the same, or they are very, very closely related. So I mean, there is a conservation law of complexity. Yeah, so you can solve problems from the Navier-Stokes point of view or from the kinetic point of view, and in the end of the day, you always run into the same problem, because this is nature. Yeah, you're not getting rid of the problem just because you study it from a different perspective. Yeah. So here we have a closure problem too, and this closure problem always means in order to compute one order, we need the next order. So, for example, now we need this here, M300. This is, of course, M300 equilibrium minus tau, time derivative of M300 plus dx M400 plus dy M310 plus d. What I'm doing, the set M301. So, or the other guys here, M210 is M210 equilibrium minus tau dt so M2, this is the one that we have here, M210 plus dx M310 plus dy M220 plus dz M211 yes. Is this correct? I think so. So obviously we also need M111. This is your homework. So now if we have them, we'll need to calculate the next order. So this is going on to infinity. Next order of moments. required. So we have an infinite hierarchy of moments. Infinite hierarchy. So how can we stop this? Use models. So inferring the higher moments depending on the lower moments. Yeah. That's an idea, but this would still, I mean, even if you know the moments, you still have to sum to infinity, which is kind of crazy, yeah? Okay, we stop it in a little bit a different fashion this time. Namely, what we are going to do, yeah, so we were drawn to the assumption that tau is small, and now we have said that, yeah, maybe tau is not small. Now we do the following. We say tau is small, but it's not 0. So what we are going to assume is that tau is larger than 0, but tau square is going to 0. Yeah? So it's small, but not so small, right? So we have something that we need to keep, and when tau equals and something that we can ignore. Okay? So in that case, what we get is that M300 would be equal to M300 equilibrium plus a term of order tau. Yeah, and this is now the integral over all of these things again, 2 pi kbt by m to the power of 3/2 e minus xi minus u square m divided by 2 kbt into xi cubed dxi plus tau. And now I put this into Mathematica, and what came out was rho u 3 kbt divided by m plus u square plus terms of order tau left. So M210, this is something that you would be able to compute yourself, because you know the equilibrium. Okay, when we just compute the equilibrium, you know what is the equilibrium for M200, and you know what is the equilibrium of M010. So for M010, it's obviously V rho, right? And for M20, it's kbt divided by m plus u square, and this plus O plus, so the rest that is not equilibrium. M111. So this you should give me right away. Now we are only interested in the equilibrium. What is this? We know that there is a rho. What else? U V W, right? Yeah, because it's the first moment in this direction, the first moment in this direction, yeah, divided by rho, 3 times rho, so one row left. And of course, because this is only equilibrium, we have a non-equilibrium part of order tau left. So now, in order to understand this simpler, we do some simplifications. So the simplifications we are doing now are not necessary. Okay? So what I mean by that is, if I don't do the simplification and I keep track of all the terms that I drop now, then I will get the same result. I will just do much more calculations to convince you in the end that these things will drop out, right? So because this makes the whole thing much longer, I'll skip over this. So one simplification that actually is necessary to understand this is we assuming that the temperature is constant. Yeah, the temperature does not change here. But one that is not necessary, so we would get the same result even if we did not assume this. We assume that u to the third power is 0, and this, of course, u, so that any third power of velocity is 0. It is convenient to assume this, but I assure you, if you do not assume this and you do go through all the calculations, then you can rearrange all these the third order terms in velocity in the end, that they just multiply with the continuity equation, and the continuity equation together is 0, and therefore they will disappear, right? So you can try this out at home and you'll see they disappear, but it's I wanted to do this a little bit faster now. Right, so this gives us for S was the reminder that we have been using before, that we have tau dx dt kbt divided by m rho, so this is basically our pressure, plus dx 3u kbt divided by m rho plus dy dy v kbt divided by m plus dz w kbt divided by m plus stuff of order tau. Now I will count the entire thing here. I will call this Sx. So there comes plus tau dy dx v k Boltzmann t rho divided by m plus dy u kb t divided by m rho plus order of tau. So because the set part of this would only contain terms with 3 velocities, which we've already dropped out. Yeah, this is why we'll have only 2 of them here, and we call this Sy, and then we'll have tau dz dx w kbt rho divided by m plus dz u kbt divided by m rho plus things of order tau, and we call this S set. So Oops, I'm making it. No. Okay, so we'll only have all the three derivatives up here, but what we see is that we have a derivative, an x derivative of u, y derivative of v, and a z derivative of w, which we almost identify as a divergence, right? The only thing that makes a non-divergence is that there is 3u here. But what we could do now is to just take to take two of them out, and here what we have here again is kBT m by rho. Yeah, so we assume that kBT by m is a constant, yeah, so that we can track this outside. And what we have then is dt rho. And here you can be reminded of the continuity equation. So when we write down the continuity equation, in this we can say that we have d in Sx, we have dx of kBT divided by m dt rho. This is what we have here, plus this part of the continuity. So now what I've done is, okay, kBT m divided by m, I've taken this out, and I've taken sorry, there must be rows in this, right? Row. Okay, yeah. Okay, I've forgotten to write here these two rows. So they show up here. So I've taken this, and I've also taken this, but here are three of them. Yeah, so here must be one left. But first of all, this thing here will go to zero. This thing here is obviously 0, yeah, because what is in here is 0. If you take derivative of 0, it's 0. So this means what is left of f of Sx is tau. Now the second derivative of x, the xx 2u, so this is still left, k Boltzmann t rho divided by m, and things of order tau square. Why order tau square? Because we have this tau times this tau here, right? So now this first part has significantly simplified, and now we can write down S again. So we have tau k Boltzmann t divided by m. And here we have dxx u rho. Now what I'm going to do is I'm picking all the second derivatives out, namely dy. Yeah, so I'm adding this here, dy u k Boltzmann t rho m. So this is this guy. Then I have dz and dz. So I have this guy here, which I write dz u k Boltzmann t rho by m. So I've taken this and this out. So we'll have just these two here. We have these two here left Okay. And you are probably looking for this too. Yeah. So I have taken only one of them. So I have one of them left. Yeah. So I have to add this again. So with tau k Boltzmann t divided by m. I've already put this in front. I should not write it again, right? Sorry that this German professor is so confusing. Yeah. So okay, I've put this already here, so I should not write it again, obviously. Yeah. So okay, I've put it here in front. Yeah. So we have dx. Now we're still having one of these left. Yeah. So we have dx u rho plus dy v rho. So this is this here, just in different order. So I put dx in front and dy backward. Yeah. Plus dz. So I'm using this here, dz w rho, closing brackets, and this goes with things of order tau square, which means I can rewrite now this S as being tau k Boltzmann t divided by m. Now this obviously is a Laplace operator, right? So on u rho plus tau k Boltzmann t divided by m into dx, and here we have the divergence of u rho. And this is the thing that we have to add to our Euler equation in order to correct it for finite tau. So, and this will be the, now what did I write? So previously we had rho dtu plus rho u into gradient of u minus 1 over m dxp. So this is the Euler equation. To the Euler equation comes this term s. So this is tau times kb t divided by m into Laplace u rho. If we had been more accurate in our derivation, we would know that we could put the rho also. We are now assuming that some things here are constant. Yeah. We could also have put this in front. Dx of the divergence of u times rho. Okay, now what we have to identify is that this here actually gives us the viscosity. Yeah, so tau times, what is this? This is the speed of sound. Yeah, square. Speed of sound square. Tau times the speed of sound square gives us the viscosity. Yeah, so now we have identified what viscosity actually is. And here we have something that in a real incompressible flow, yeah, will obviously disappear because it's the divergence of u. Yeah, so we would not have this, but if the flow is compressible, we'll have this term. And now this is just a diffusion term with this viscosity, and this equation here is of course called the Navier-Stokes equation. And with this, we have discovered that we can derive the Navier-Stokes equation from kinetic theory. So, I mean, this could be an end in itself, yeah, that you just learn how to get the Navier-Stokes equation out of kinetic theory. But we do this of course, for a particular purpose, namely the Navier-Stokes equation and the Boltzmann equation, they are not equivalent. Yeah, we see that only under certain assumptions, yeah, in a certain limit, we get the Navier-Stokes equation out of the Boltzmann equation. So you could actually say this is a tangent of the Boltzmann equation for vanishing Knudsen number. Yeah. So the Knudsen number needs to be vanishingly small, but it must not be zero. Yeah. Now this is an important thing. And the other thing that we learn from this is to which order in this moment hierarchy do we have to keep our moments in order to get to the Navier-Stokes equation. Now this will turn out to be important when we go tomorrow to the discrete velocity model, because this tells us now that we have what moments we have to capture. Obviously, we have to capture zero moment, first moment, but we had to take the second moment into account, right? The third moment, what happened to the third moment? The third moment, we only needed the equilibrium of the third moment. Yeah? So by this procedure, we recognize when we want to solve the incompressible Navier-Stokes equation only, yeah, we can do with up to third moments as long as the third moments are correct in equilibrium, and up to the second moments we need the equilibrium and non-equilibrium part. And this will now tell us how we can discretize our velocity space such that we keep enough moments in order to use the Boltzmann equation, a simplified discretization of the Boltzmann equation that solves the Navier-Stokes equation. Yeah? So this was the purpose for looking into this derivation. Okay?
Isn't it the equation dimensionally inconsistent because of the
okay, so
mass term?
Dimensionless inconsistent. Okay, they should now be, so in this case, they should be dimensional consistent because this rho is just 1 over the volume. I believe it should be consistent. So
if you just consider the temporal convection and the pressure gradient term.
The temporal
convection and the pressure gradient term.
Yeah.
The pressure gradient term is multiplied with a factor of 1 over m.
Yeah.
So m has a unit of kg. So it's
yeah.
consistent.
Yeah, but in the pressure is mass because it's Newton per square meter. The pressure is Newton per square meter. Yeah. So Newton is kilogram per meter, kilogram per mass per acceleration. So it's kilogram per meter per second square.
No, just by looking at the equation, we can retrieve Navier-Stokes equation only when m equal to 1.
M equal to 1. No. Then you would end up with not having. Then you would have kilogram in the P. So because there is no kilo. Okay, I agree. This is confusing because this rho here has the units 1 over cubic meter.
Oh, it's not kg per meter cube.
No, this is, you remember, because this is particle density, not mass density. Yeah.
Okay, got it.
Yeah. So okay, I totally agree that this is confusing. Yeah. So this is right. So if we write this in as you say proper density, which comes in kilograms per cubic meter, then there is no m here.
Yeah.
That's true. Yes.
So which one is more accurate? Is the Navier-Stokes equation or this model?
What is more accurate?
Hmm.
You mean from a physical point of view?
Yes.
I mean, this is what you mean by that model. So this model is this is the Navier-Stokes equation. Yeah, so this is the Navier-Stokes equation. So here this is the same accuracy as the Navier-Stokes equation.
Yeah, but actually
So you mean the Boltzmann equation?
No, we are neglecting the higher order terms here.
Yes, I need to neglect. Okay, so in the Boltzmann equation, I need to neglect a lot of information in order to end up with the Navier-Stokes equation. So we went actually through two steps. In order to get to the Boltzmann equation, we had to neglect all the information on the individual particles. So what particle is where? Yeah. So we just said all particles are the same. Yeah. So we made a lot of assumptions to go from the molecular reality to the Boltzmann equation. Yeah. Now we make a lot of assumptions to go from the Boltzmann equation to the Navier-Stokes equation. So there is, of course, a clear hierarchy of what is the higher truth. Yeah. So the molecular description of everything is, of course, much closer to the truth than the Boltzmann equation, and the Boltzmann equation is much closer to the truth than the Navier-Stokes equation. Yeah. So you learn potentially in your classes the Navier-Stokes equation is what governs everything, but the Navier-Stokes equation has its clear limits. What it can actually do. So one example that I think I have on one of the later slides, but I can just talk about this now here. They're very simple cases, everyday cases where the Navier-Stokes equation fails. One thing that the Navier-Stokes equation cannot do, even though things like open form can do it because they are numerical approximations where you do mistakes to eliminate other mistakes. Yeah? In the Navier-Stokes equation, it is not possible that the raindrop that is dropping into an ocean would merge with the ocean. Why so? Because the Navier-Stokes equation does not know anything about small length scales. Yeah, so the Navier-Stokes equation would assume it's useful for all length scales. So if a droplet gets closer to another droplet or to an ocean, yeah, so then the pressure between these two surfaces will just rise, and at one point it will be so strong that it will be repelled, right? So it is impossible, and mathematicians, I have seen people applying for a job as a mathematician professor, talking in their speech about this problem and that it cannot be solved. And for them, this is a terrible mystery. How can this be? The Navier-Stokes equation claims that two surfaces can never touch. Yeah, because if they get closer and closer and closer, the pressure gets larger and larger and larger, and finally so large that they will always be kept apart. This is the solution of the Navier-Stokes equation. But this ignores that when you put two surfaces closer and closer and closer together, that the Knudsen number suddenly will no longer be small. Yeah? And everything that we've discussed here is only true if the Knudsen number is small. Because if the Knudsen number is not small, then tau square is not 0. And then this derivation breaks down. And the Navier-Stokes equation is simply not valid for a droplet dropping into the ocean. So why can open form do this? Very simple, because open form uses a discretization. That means, in a sense, it has a Knudsen number. Yeah. So it is simply the droplets. Yeah. So the droplets cannot get. So when the distance becomes smaller, then the grid size of your open form grid, then it can no longer solve the Navier-Stokes equation. And they simply say, okay, now they are together. Yeah. So in principle, and this would happen if you use an adaptive discretization. Yeah. If you insist, I want to solve the Navier-Stokes equation, and I use an adaptive discretization. So your droplet gets closer and closer and closer. You'd simply refine the grid infinite forever. Yeah. And it will simply keep the two things apart forever, because this is the solution of the Navier-Stokes equation. So this only works, so you can only solve this problem with the Navier-Stokes solver, because the Navier-Stokes solver is incorrect. Yeah? It has this numerical error. So this is one of the things that where Navier-Stokes equation is not working. Yeah? So the assumption always is that the Knudsen number must be small. Now, that the Navier-Stokes equation is small is a less important assumption. So you can also derive a compressible Navier-Stokes equation, yeah, where you take more things into account. But we simplified this to the incompressible Navier-Stokes equation. So if this is not the case, then tomorrow in the morning we have another lecture on, I believe, discrete velocity models. And in the afternoon, we will have a practical session that we would actually have had today. Yeah, so it would be a good thing if, so we'll have a demonstration actually where you yourself don't program, but we'll have a hackathon in the next week. And for this reason, it is you should get prepared with your own computer, because you have to get something to program yourself. So maybe you have your laptops at the ready. Tomorrow you don't need them necessarily, but you will get some code and you will do something into the code by, I think, Friday. Yeah. So you get the code by Friday, and then next week we'll have this hackathon.